When you pour water from a cup and it splashes out instantly. Pour honey from the same height and it creeps down in slow ribbons. Same gravity, but wildly different flow. Why? The answer is viscosity, a fluid's internal resistance to flowing. Formally, viscosity is the ratio of shear stress to shear rate, how strongly a fluid pushes back against being deformed, measured in Pascal seconds. Think of a fluid as stacked layers sliding past each other. Viscosity is simply the friction between those sliding layers. Newton pictured this with two parallel plates and fluid trapped between them. The bottom plate stays still while the top plate is dragged sideways. The fluid touching the top plate moves with it. The fluid touching the bottom stays at rest. In between, velocity changes smoothly from layer to layer. The force per area needed to drag the plate is shear stress, written as tau. The rate velocity changes across the gap is the shear rate, du over dy. Newton proposed a strikingly simple relationship between the two. Tau equals mu times du over dy. This is Newton's law of viscosity. Mu, the viscosity, is just the proportionality constant, a property of the fluid itself. Plot shear stress on the y-axis against shear rate on the x-axis. For a Newtonian fluid, this plot is a single straight line through the origin. The slope of that line is mu, and it stays constant no matter how fast you shear the fluid. Water, air, and thin oils all behave this way, hence Newtonian fluids. Many everyday fluids refuse to follow a straight line. Ketchup barely flows at rest, but squeeze it and it thins out. This is shear thinning. The curve bends downward, flattening as shear rate rises. Paint and blood behave the same way. Cornstarch mixed with water does the opposite. Stir slowly and it flows like liquid. Punch it hard and it turns solid instantly. This is shear thickening. The curve bends upward, steepening as shear rate rises. Some fluids will not flow at all until you push past a threshold. Toothpaste sits still on the brush until you squeeze it. This is a Bingham plastic, needing a minimum yield stress before it flows. Put all four together. A straight line for Newtonian, a curve bending down for shear thinning, one bending up for shear thickening, and a line starting above zero for Bingham plastic. One law, four behaviors, and a world of everyday fluids explained.